Right. So first talk is going to go over the sort of foundational distributed systems primitive called Merkle trees, motivate why you should care about it, and sort of explain why Merkle trees and recursion schemes sort of dovetail together. Second talk, also this morning, is going to give people a primer on recursion schemes and how to sort of work with that structure, how to do like a simple diffing algorithm. Then Friday, that'll be the second two talks, we're going to go into how to make it sort of robust, how to lazily diff two trees, how to use the cryptographic hashes to short circuit, basically all the stuff you need to make it performant. This is going to be the motivation and intro to the underlying primitives. Second two talks are going to be just sort of how you actually make it work, and then how you derive sort of generic abstractions from that you can use for arbitrary Merkle trees instead of pinning it to just directory trees. So that said, let's jump in, right? First thing you need to, right. Give it one more minute.
Oh, go ahead.
Oh, awesome.
Possible to
Oh, perfect. Right. So first thing you need to know for Merkle trees, this is sort of like the foundational primitive that they rest on, cryptographic hashing, right? You have a cryptographic hash function. The common one all of you have probably heard of is SHA-256, but they have a couple properties that are important, right? Essentially, they're a black box. Your text goes in, your hash goes out. They convert arbitrarily sized imports into fixed size hashes. So it doesn't, whatever you put in, 1 byte or 10,000 bytes, you'll get out a hash of the same size. The text cannot be recovered from a hash. They're deterministic. They're collision resistant. Small change to the text will result in a large change to the hash. And they sort of act as a digital fingerprint, right? So like if you have two large structures with the same hash, you don't need to compare the structures line by line or byte by byte. Because they have the same hash, you know that they're the same. Like hash collisions exist, especially in weaker hash algorithms, but we're talking like run a computer for the age of the universe and you might find one type things. It's not something you need to worry about. So this is what it looks like in Haskell, right? So I'm just pinning, instead of having hash as an arbitrary hash function, it's specifically pinned to digests of SHA-256, just because that's the one everyone's familiar with. That's the one that Bitcoin, I think Bitcoin uses, Git uses, Mercurial, et cetera. And the hash function, you just go from a byte string to a hash. Simple so far. So this is the thing that everything rests on, but you don't need to know like the internals. You just need to know that there's a magic black box that gives you a sort of digital fingerprint of a fixed size for an arbitrary sized byte string. Right. So Merkle trees. This stole this from Wikipedia, borrowed. So you can sort of see here, right? They're a tree, which every node is annotated with a cryptographic hash of that node's text, and that includes, so for the leaf nodes, it's just the node's data, but for every node that has a recursive link, it's the hash of the node it has a recursive link to, plus whatever information's here. And then that just rolls all the way up, right? So this just has the hash of L3, this has the hash of L4, this one has the hash of this, and so on, right? So if something changes here, it would change the hash, it would change this, it would change this as hash, and it would roll all the way up to the top of the tree. But this branch would stay the same, right? Because nothing changed up here. So this would be the same. If this was changed, all this would be different, this would be the same, this would be different. Right. So Merkle trees. It's basically just anything you can do it with a tree. You can apply this structure to any tree as long as you can hash each layer and roll the hashes all the way up. So there's a lot of benefits. Like, why should you care about these, right? So the main ones, you have immutability. Like if you have the same hash, which is short, right? You can share that, you can put it in a tweet, you can just store that in whatever system. You know nothing's going to change, which again, modulo difficult cryptographic problems. Like you have a guarantee nothing's going to change. And the thing that we're looking at here, one of the most important properties, you get constant time equality checking, right? Because you just compare hashes. You don't need to compare subtrees. So what that gets you, that actually gets you like a really important property with regard to diffing two trees that I wanted to like really just highlight in the first few slides. So let's say you're like Facebook, you're Google, whatever, you have a monorepo. You have millions of files, you have like maybe 5, 6 directories deep, and it's just, they're huge, right? And you make a change to one file. You can't feasibly compare every file in the new directory tree versus every file in the old directory tree. Like, it's just not feasible. But what you can do is you can just compare the hashes of every subtree, and you can avoid looking in any subtree where the hashes match, because you know you don't have to go down that subtree. You know they're equal. So it actually gives you O n log n performance with regard to the number of changes instead of the number of files, right? And that makes diffing directory trees actually like feasible in a way that they wouldn't be. I don't think anyone's on that table, by the way. It's just being used for paper storage.
Yeah, there's still a couple of spaces.
Oh, sick. Awesome. Yeah, so it gets you that. It gets you lazy traversal. So this is in sort of a distributed system sense. Like, imagine you have some like file store that has a bunch of like individual nodes with the recursive links subbed out for hashes, and you just want to look at like one subdirectory in your tree. You can like just pull the parts of the structure necessary from the store and leave any hash links unsubstantiated if you don't care about them, right? So you end up actually being able to work with very large structures and only looking at the parts that you care about, which is great. You get structural sharing, right? And this is where I actually wanted to bring something up. Merkle trees versus Merkle DAGs, right? Directed acyclic graph versus tree. We can just consider everything as a tree because we're working in Haskell and the data structure is going to be more like tree-like. But if two branches of a tree have the same contents, they'll have the same hash, they'll only have to be represented once on disk in your file store, in your distributed system, etc. And last, easy caching, right? I'm not really a distributed systems person, but if you can reduce your problem down to storing hash-addressed blobs, you're in a really good place because you never need to do cache invalidation. You know that some content will always have the same hash, so vice versa, that hash key will always point to the same content. Quick break for questions. Does this all make sense so far? No raised hands. Awesome. Oh, okay.
Is concatenation of cryptographic hashes is cryptographically secure because we rely on it implicitly?
The concatenation of cryptographic hashes?
Yeah.
Yes, because you just reduce the cryptographic hashes down to a byte string, like sort of like via like byte string show or something. Not really that. And then you just make that part of the text that you then hash. So you're hashing at each level. You're not concatenating the hashes and just returning that. You're concatenating the hashes and then you're hashing the concatenation.
Well, there can be a problem because hash may not take all possible values for all bytes, so you reduce input space, and this may lead to reducing output space, which in turn leads to increasing collisions.
Honestly, maybe. I don't know enough about cryptography to really address this in this talk. I would love to talk to you about this after. This is the thing that like a lot of actual projects use, so I'm like medium confident that it works. Yes.
Please explain why is it n log n? Is n number of changes or size of tree or?
Oh, sorry, yes. If you didn't have the cryptographic hashes on every node, you would have to go down the entire tree, and it would be n log n with regard to the size of the entire tree, right? But if you have the cryptographic hashes, you can avoid descending into branches that haven't changed. So it's only n log n with regard to the number of changes.
Compare two structures of size n. Why is this comparison to the n log n?
Because you can avoid looking at large parts of the structure. This is something I got from a friend of mine who works with distributed version control systems. I don't really want to dive into I'm not going to be deriving this big O notation here. It's just to indicate that instead of having to compare every structure in a tree to do diffing, you just have to compare the branches that you know changed, the branches where the cryptographic hash differs, and you can avoid comparing any branch where the cryptographic hash is the same. So you get a significant performance boost. That's sort of the takeaway. I'm medium sure this is right. I'd love to talk about it after, but really the takeaway is you do get a significant performance boost. This is how like Git and Mercurial and et cetera can make diffing like feasible for large repos. Is that cool? Right. So distributed systems, right? These are used in like a lot of distributed systems, like everything since 2005. unsourced quote because I heard this in the grapevine, but everything since 2005 has at least considered using them, right? So here's a list of things you've probably heard about, right? Git and Mercurial. I don't know if SVN uses them. I don't want to know. Talk about this later if you know about SVN. Everything on the decentralized web, right? BitTorrent uses them. Bitcoin and every blockchain project is essentially just a Merkle linked list. IPFS is a Merkle DAG, like a Merkle graph. Build tools, right? NixOS kind of, because you're not hashing the actual binary that you output, you're hashing the build input. And then ditto for like Buck and Bazel. Right, like the point of this slide is that they're sufficiently broadly used that they're worth looking into, they're worth caring about, and what I hope that you'll get out of this is a set of tools and concepts that makes it easy to prototype new systems using Merkle trees. Like if you have some idea and you're like, oh, what if I Merkle this? This should make it easy enough that you can like take an evening and throw it together instead of needing it to be like a non-trivial algorithmic challenge. So I really am hoping that people come out of this and they're like, oh, that side project, it's feasible now. Like if you want to build your own BitTorrent or something. Right. So here's a little note on how they're implemented. I sort of touched on this before, but when they're stored in a store, they're stored as individual layers, right? So you'd have like, you wouldn't store this entire structure. You would store just L4, or you would store just this node. And instead of having a recursive link and including this structure, you would just have this node with the hash, right? Like a hash pointer. And that hash pointer could then be dereferenced to grab this structure all the way up the tree. Cool. Right. So here's what we're going to be zooming in on. We're going to be building sort of a core component of a distributed version control system, which is lazy diffing. If we have time, I'll also show you how to do lazy merge. It's kind of cool. These both are like 100-ish lines of code, and like you get all the Git primitives and like a couple hundred lines of code, and then they like rely on some abstractions and et cetera. Yeah, and as before, you get quick diffing, you get structural sharing, right? That sort of touches on the Merkle tree versus Merkle DAG. Like basically if you have two branches of a DAG or whatever, and they just point to the same hash, you don't need to store that twice. You just have like a hash-based cache. You just have the same entry. So this is huge in Git, for example. Like if you have a bunch of commits that have like the same root tree with only one file changed, you don't need to store the entire root tree every time. You just store the new file. And that is, you know, that makes these things actually work. And again, simplified caching, right? You never have to do cache invalidation, and you will just make any distributed systems people you work with happy, because like this is like reducing a problem to an easy form. Cool. So let's get into Haskell code. This is, you know, it's a Haskell conference. People like Haskell. This isn't a cryptography conference. I'm definitely not a cryptographer. Right. So here's sort of what we're going to be working with. It's a directory tree. We're leaving the hash annotations for later. Those are going to sort of like come out of the subsequent slides and sessions. So notes, right? Like in Git, the top level directory has no name. So you just have a directory tree, a dir tree, with a list of entities. And each entity is a tuple of file path. That's the name of that entity. Not the name of the full path down all the way, just like the name of that file or subdirectory. And then you have a file tree entity. Let's just ignore that for now. You have a file tree entity, and for simplicity, we're storing the files directly inline. You wouldn't actually do that. That's inefficient, it's bad, but it also makes it fit on a slide, and I have a repo where it doesn't do that I'd be happy to go through with everyone after. We'll probably get to that in like the 4th session. Cool. So it has the files, which is just an inline string, or, and yes, I know it's a string, it's not text, etc. Once again, C fitting on a single slide. And then you have a directory entity, which is just a recursive link back to dir tree. This is the subdirectories, right? Cool. So that makes sense so far? Awesome. So let's like actually look at some of the stuff we need to do to actually represent like the different formulations, like where it has the hash pointers, like the one we actually store on disk, right? So recap, you have your hash. It's just the SHA-256 digest, right? You have a hashable directory layer. It's, you know, it's basically the same, hashable file tree entity instead of file tree entity. It's, you know, some duplication. Again, string inline. But here, the only change is the recursive link. Instead of being a directory tree, it's just a hash. It's just a pointer, right? And yes, I know it's Haskell. We have pointers anyway. Just you know, work with me. Right. So That's not very good, is it? Because we have like the same structure duplicated like entirely. So we're going to try and do better because this is Haskell. We have all the abstractions. So what we're going to do is just take that single thing that is the only thing that changes between the two, and we're going to put a type parameter there. Talking too fast. Right. So that's A, right? And you have the A just down to a file tree entity, and here. So the hashable layer, it's really simple, right? Again, you have the hash here, and you just have a type, right? Hashable directory layer is just a directory layer with the recursive parameter substituted with a hash. Makes sense? Cool. So here's where this gets problematic, right? So we want to have the recursive case, and like at a term level, this, we kind of know what we want, right? We want the directory entity to be like another directory layer and so on as long as we have directory layers. But like, what type is that, right? Directory layer, and it just keeps going. You can't represent that. Like, if you really wanted to, you could have it like bottom out at void, but like then you have a different type for the different size of tree, and like no one wants that. So here's what we're going to do instead. So we actually use a type level fixed point, and I want to stay on the slide for a bit because this is one of the core concepts. Type level fixed point, right? It's parameterized over f. And it's just an f of fix of f. This lets us do that like recursively stacked sort of single structure with a type parameter, and it lets us do it without the type being ridiculous, right? So now a directory tree, we know its type, it's just fix of directory layer. And this is kind of what it looks like at the term level. Note that we now have a good type for it. You just use fix interleaved between every directory layer, right? Does this make sense to everybody? Awesome. Cool. So we've sort of stumbled backwards onto recursion schemes. This is a really powerful abstraction. So it generalizes over fold and unfold and some slightly more like powerful like versions of those in the same way that for loops generalize over gotos. And like there are actually some papers that essentially argue that just as you really don't want to be using gotos, you don't want to be doing like primitive recursion where you pattern match and recurse yourself. You just want to use this formulation that lets you not have to worry about that. I'm not that dogmatic about it, but it really is quite powerful. And if you can do the little bit of extra work to get your thing into like the fixed point formulation, you can get some nice stuff out of this. And next talk, the next session is going to be all about how to work with these. So before we do that, let's motivate it a little bit, right? So let's look at some of the core stuff that we want to do with a Merkle tree. So first, we want to hash a single layer of it and then roll the hashes up all the way to get the hash of an entire tree. Like, you hash the leaves, then you go up to the nodes that have pointers to leaves. You hash that with the pointers substituted for hashes. You keep going until you have a single hash that identifies the entire tree. And we're doing ASON encoding because I'm lazy. We can just get some byte string. We can hash that byte string. I don't really show the hash function here because it's just a bunch of like ping-ponging between different byte string formulations and stuff. It's not interesting, but all right. So you get this abstraction catamorphism called kata. This generalizes it over folds, right? This is a recursion schemes thing. We'll be deriving it in the next talk. Before we do, look at how convenient this is, right? You can turn something that hashes a single layer with the recursive pointers being hashes, which is sort of just naturally falls out of Merkle trees, and you can turn that into something that hashes an entire tree just with catamorphism, because it takes a function of fa to a, which is, dir layer hash to hash. It applies that to a fix of f, a fix of dir layer, and it gives you a hash, right? Cool. You can also, let's say you want to write a directory tree to a disk, right? So let's say you have the single function. This is a bit simplified. You're just using ASON again because it's convenient, deriving serialization formats. Probably shouldn't do that in prod code, but it doesn't matter. You have some base directory, and you're just like dropping into that. You're dropping a bunch of hash addressed files where you use hash layer from before to hash an individual dir layer hash. Then you just encode it, and you write it to a path derived from the hash, which I'm not showing the hash to path function here, but if you clone that repo, you can look at it. And again, you can just use recursion schemes to do this for you, to do the hard part for you, which is running that function over every layer of the tree and sort of rolling it up, sort of folding the tree up into a single value while running a monadic effect. So here, instead of FA to A, it's FA to M of A, right? And up there, dir layer hash to IO of hash. IO is a monad. We have a traversable for F because, you know, we just derived it. I didn't show the deriving lines in the data stuff, but it's there, trust me. So again, right, you just get this like really simple formulation where you can write an entire directory tree to a path, just given this function to write a single layer to a path. I'll be dropping into the REPL in the second session. There'll be a bunch of examples. This isn't just going to be slides, trust me. Cool. So again, right, you want to oh, sorry, we've got a raised hand back there.
Can you switch back one slide?
One more?
Yeah. So you have this hash layer.
Yes.
Takes something which contains a hash.
Yeah, it takes a directory layer parameterized over hashes, right? That's just a directory layer where every recursive link to a subdirectory is instead a hash of that subdirectory. And you hash that, and that gives you a hash. And you can use catamorphism, kata, to fold that over the entire tree.
Yeah, well, that was my question. So if you look at the typing of kata, you fill in F for dir layer and A for hash, right?
Yes. So dir layer of hash to hash.
Yeah, so that's a function which takes something, something hash, produces hash, and then you give it a fixed F.
Yes.
It produces a hash.
Yes.
But where does the initial, it seems to just magically create this A.
Oh, I know. It's really cool. We'll be deriving kata in the next session. It seems like magic, but once, like, the functor is actually key. If you come up with this on your own, that'll be really cool. But seriously, in about half an hour, I'm going to be going over in detail how to write this function. It does seem like magic. It's just like a cool insight in the same way that, like, fold seemed like magic, like when you're all learning Haskell. Then you're like, oh, that works. That generalizes over this entire set of patterns. We'll be going over this soon. That cool. So this is like the motivation. This is like why you should care about recursion schemes, because like these are just some basic functions that you're going to want for working with Merkle trees. And given those basic functions, you can just do a lot of cool stuff. So like reading a layer, right? You have some base directory for the thing. You have a hash. You get to an IO of dir layer of hash. This is basically like the dual of writing a layer. Right? So instead of FA to M of A, you have an A to M of F of A, and anamorphism is sort of just a generic unfold, and anamorphism M is generic, like, monadic unfolding. So yes, I know these seem like magic. You're summoning the fix F from the A, and the A doesn't show up in the result. We'll be going over that soon. It'll make sense, I promise. So again, right, you read an entire directory tree from a base dir, and which is just like the place in your file system where you're storing these things. And you know, you probably shouldn't actually fail in production code. You would want this to be like except T something instead of IO, except T IO instead of IO. But like again, in service of fitting on a single slide, right? Yeah. So all right, cool. We have a bit of time. Let me actually hop in the REPL and like show you that some of this stuff actually works, right? And then we'll go on to deriving like catamorphisms. Yes. I am running Windows with a Linux subsystem. Please don't make fun of me. I just got this laptop like a week ago, and I didn't want to be dealing with Nix while I was traveling, which I will do that later, trust me. So we have
We need it larger and more contrast.
For the color button, please.
And also maybe we should turn off the lights.
Turn off what?
Lights.
Oh, yes, please. If someone can handle the lights, that would be wonderful. Sorry, this is going to take a second. Oh, beautiful. Right, is this good for everybody? Sorry. Yeah, so we have you know, my directory tree, which is the same thing, my dir tree, which is the same thing from the slides. So we're just going to hash that, right? We have hash layer, which is as above. We have hash dir tree. So we can do that.
Can you shift the single user ID bit?
Which one?
Well, the one from the driver.
The left half of the left screen.
Oh, I see. Like this?
Much better.
Oh, perfect. Sorry?
It's like the left side is cut off.
Oh, it is, isn't it? Thank you. Yes. So let's just do, is this good?
Yeah, that's good. That's good.
Yeah, can we have more contrast though? I don't know, black and white or something
Yeah,
like
the gray
that.
is a little tricky, this is for sure.
Absolutely. Let's see if this is good. Is that good?
Yeah, that's great.
Perfect. Yeah, actually, I'm just going to use that one from now on. Cool. So, all right, so we're hashing the directory tree. Let's like show that this actually works in the REPL first. Like, it's going to roll up the directory layers inside fix, and then just hash those, then hash the top level. So, I'm going to import some things. I'm going to reload because I renamed that. Right, so it just gives us a hash, and that's, again, it's rolling the hash function all the way up, hashing every subdirectory, then hashing the top level. Oh, it's 1025. Cool. Yeah. So, right.
Maybe can you show an invocation of just hash layer over a single dir layer?
Absolutely. So let's just do that over dir layer. So you can hash a single layer like that, right? And then you would imagine, say, you have another layer. Let's actually have that. No, that's not actually monadic. Sorry. So instead of a file entity, now you have a directory entity, and the directory entity ends up with a hash, right? So you can see sort of how that would roll up the hash in that example. Let's actually look at how that would work if you have something on the disk, right? So we've got a directory called temp/file store. We're going to be just writing some stuff to that. So let's take the thing that we actually just defined, the foobar file entity baz, and let's see, we have to actually import something. All right. So we're going to write a layer to /temp/file store. Sorry. I really do need to switch this over just to proper Linux. This is what I get. So let's actually do that with the dir layer that we have above. And yeah, you can follow along with all this if you clone GitHub /Bekinski /Merkle schemes. Let's actually just get that on here. And run stack rebel talk. And there's some other stuff in that repo, like kind of a bunch of stuff that you don't really need to build for this. So just run stack rebel talk, and that gets you sort of the simplified slide fit versions of everything. So let's write this layer to the directory store. So we get a hash, right? That hash should exist in the directory store, which it does. And we can look at that. And we're going to drop it through a... Oh, yeah, sorry. I changed it in the other one, but it's not global, apparently. By the way, I know I talk too fast sometimes, so if I'm doing that, if anyone has trouble understanding, or if I'm zooming through stuff that you think needs to have more time spent on it, please do tell me. That would be very valuable feedback. Yes. So now this should be sufficient. Cool. So we're just going to cat this file and pipe it through something that formats our JSON for us. And we can see it's the single direct subdirectory called foobar with this hash as its pointer. So crucially, we've like put our store into a bad state because there's not actually an entity there for 629, et cetera. But like we have the thing that we hashed to make that, so we can just hash that. Yeah, so we know it just looks like this. So let's actually drop that into the store. Right, so it gives us 629, et cetera, which is the same here because that makes sense because it's the same structure. We hashed it in the REPL, and now here all we're doing really is hashing it and dropping it into the store. So you can see it now has both. I'm going to cat that one just to prove that to y'all. And yeah, you can see this one doesn't have any recursive subdirectory links. It just has the file entity. So now we can actually use read layer to read from the hash of the top level.
What does this JSON represent here?
This JSON is a, sorry, yes, thank you. This JSON is a JSON encoding of the file tree entity, or the directory layer with the file tree entity inside it. So the top level entities is the directory layer, right, with the tuples of file path and file tree entity here in the list. And then each thing is either a file tree entity, which is either a file entity, which is just an inline string, which again is simplified for the purposes of this talk. It would be a hash pointer to a blob in a real system. And the contents, which is BAS, or a directory entity, which is a recursive link. And in the version we hash, that recursive link is to just a hash of a subdirectory.
Okay, so the one you're looking at here, is this a subtree or is this the root of the tree?
The one we're looking at here is a subtree. This is the one that just bottoms out with a file. And the previous one is, this is the one that actually contains that subtree. This is the one where it's, instead of a file entity here, it's a directory entity, a dir entity, and it just has a hash. This hash points to here.
Okay. And each node of the tree is just stored flat at the top level of our actual file system?
Yes. You could also use this in a key value store. You could do it on S3. But yes, every node is stored flat. Every node's key is the hash of that flat node. Cool. So let's actually, we need the actual top level hash so we can read it. Let's get that. Top level hash. And we're going to actually use this to read everything back, and that'll just sort of prove that this is like sane-ish. So top level hash, as we expect, it's E7, et cetera, as it is here. So we can just do a read dir tree for that, and /temp/ file store, top level hash, and we get a directory tree back. Did not define a show instance for that, but you can notice it didn't blow up, and we can write that back to another store just to prove that it's like sane. Yeah. Quick question, that clock and my computer are showing different times. It is 10:30, right? Not like 10:45? Cool. Right. So we can actually hop on to the next slides. I think that might take a bit more time because that's actually diving into how recursion schemes work. And that's going to be fun to go through. That's going to actually, I sort of feel like I've motivated a little bit of caring about this, and we can now actually look into how it's derived. Full screen it again. Seriously, I apologize for the windows. It's going to change soon. Right. So, we're going to use recursion schemes just to work with a really simple concel style list of the sort that you've probably all seen in like various examples. Right. Just to recap, you have the type level fixed point of some f with the recursive link just being a fix of f. And if you want to represent a list using that, right, you're going to call the type, we're going to call the type listf because it's, we have to have the functor for it, and we also want to use that name for the fix point of it because that's what we'll actually be working with. So it's just a con cell with an A and a B. The A is the actual element stored in the list, and the B is the recursive link to the next, to the rest of the list. And you can notice here there's a nil, so there is like an ending case, like a terminating case. And we're going to call just a list A a fix of listf A, right? This is what that looks like at the term level. So you have a fix of cons, it's an int list, a fix of cons 1, then it has the recursive link B, that's a fix of a cons 2, recursive link B, fix of nil. So does that all make sense, just how that would be like defined as a term and like compile and such? Questions? Cool. So this is where it gets interesting, right? I told you we'd be generalizing over fold, and someone asked a question about how you get from f of A to A to something that doesn't have any f in it, or vice versa. Yes, it's kind of magic, right? So this is how it works. Catamorphism. So you have to have a functor constraint that's used for the f map. That's where the magic comes from. You have an algebra that's just of type fa to a. That's sort of collapsing a single layer of the recursive structure into itself just to get an a. You have a fix of f. That's the thing you're collapsing. And then you have an a. Now, yes, there's no a in here, and you get an a out of it somehow. Kind of magic, kind of not, right? So I've annotated each of these with the type at each level as you like go down through the function tree, or the function, yeah? So you can see that you start with a fix of f, then you run unfix, which really just gives you the f of fix of f here. Then, this is the magic, you f-map over the inside of that. It's a fix of f, right? We know we have a catamorphism. We can turn a fix of f into an a. So you f-map over that. So you turn the f fix of f into an f of a, right? And then we have an f of a. We have that algebra. Then you collapse that last layer down. So this is a bit crazy. It does actually work. And yes, we're going to just show a super simple example of it on the next slide for turning our sort of bespoke list type into just a boring Haskell list, or alternatively, a normal Haskell list. Right. So the for-al constraint is really just so we can get a down here. And this function, it turns our list with the console branch and the nil branch, list of a into a list, into just a Haskell list of a. Right. So the algebra is kind of the magic, right? It's a list f. The first parameter is simple. It's just the element type of the list. And the second one is the thing that we're folding down into. So with this algebra, we assume that at every level, we've already computed over every subsequent level, and then we just handle that. And the reason that like eventually works is we eventually hit nil, right? And there's no more recursive links at nil. So we can actually just turn nil into an empty list, and then we have a con cell, the other case, where it's an x and an accumulator, and we just, and the accumulator is the list of a, where we've computed it for everything in the list already. And here you can see we just, we prepend x to the accumulated list. And
sorry, can you turn back to the other slide and explain it again, because I still don't get catamorphism.
sorry, yes. Diagram of what?
It's basically you're chasing down the diagram from like A, B, and then like instead of going this way, you're actually going.
Let's just stick on this slide for a bit. Okay, so working it out on a piece of paper, right? We have paper, that's good. So let's imagine you just have and this is an instance of our list f type, right? Can everyone see this? Cool. So the first application of it, it's going to remove this fix. It's going to have a cons 1 fix nil. It'll f-map the catamorphism over that, then it'll apply it just to fix nil, right? So you fmap over nil. That's a no-op because nil doesn't have any recursive links. With me so far? Cool. So you fmap over nil. That'll just give you, with toList as before, that'll just give you this. So what you then have is cons1 this, right? After you've fmapped over this, you just consume this with a kata.
So don't you have to, how do you unify the list f and the list types? Like right now you've got cons, because you've got the list f, cons, and the list nil.
Right, this is like a partial state. What we have here is actually the f of a here, right? This is what we have after we fmap over it. So this is something that we can then apply the algebra f of a to a over. So we apply that to this, and then we just have list of 1, right? Because we would just prepend 1 to an empty list, so we just get list of 1. Does that make sense? Not really. OK. What part doesn't make sense? Sorry. I would be really happy to talk over this in between the two sessions. This does work. I know it seems kind of like magic, but if you can just assume that you have a function called catamorphism with this type signature that does this thing, you can do some cool stuff with it, and the sort of intuition will come after a little bit. Right. So.
May I offer some fresher games intuition, because I had exposure to recursion schemes recently, so maybe can you go back to the first slide?
Yes.
Yeah, so how I understand all those things, the f in here is it's a factor, right? It's our recursive structure that we use instead of the naive data type that we would use. It has a recursive call in it, and that's what makes it a factor, basically. What we do in the kata function is at first we've got a fixed version of our structure. What we do first, we unfix, so we unwrap one layer of our recursive structure, and we receive it in a functor, in that functor that we use for the data structure. Since we've got a functor, we can fmap over it. And what do we fmap? Well, we want to receive in return an f of a, and we happen to have a function that does just that. We are in the process of proving that it does what we want it to do, yes, but we use it recursively, and that's, by the way, the only place where the direct recursion needs to happen, the framework itself, right? So we fmap with the kata and the algebra we've been provided with. By the way, the algebra is a function that, given a structure in that, so our functor, it unpacks the value held by the functor.
It just collapses one layer. It's an f of a to a, right?
Yeah. So we receive from the fmap an f of a, and what's left is just computing the result of the algebra for the whole subtree that we have.
Yeah, now it makes sense.
Awesome. Thank you very much. It took me a while to get that intuition to stick, and as always, it's easy to forget how long it seems a bit like magic. Yes. So let's actually just prove this works. Just a bit of sanity checking, right? We can actually turn the list into a proper list. And I really do encourage you to play around with this a bit, just to convince yourself that it works. Right, it just has 1, 2, and as we have in my list, it's just fix cons 1, fix cons 2. It's kind of just an ungainly way of writing a console list, but we will get some cool stuff out of this. Right. So now we're at 1044. Yes. let's just work with Kata a bit more. This is the same thing we're using with HashLayer. So let's go back to, right. So it's in the same way that we're taking a list f a and then the recursive parameter being the thing we already want to compute. We're taking a directory layer with the recursive parameter being a hash, which is what we already want to compute. We assume every lower layer has already been handled for us, and then we just compute the one layer into a hash. Which it's just like a really simple way of writing a lot of recursive functions. You don't need to do all the bookkeeping yourself. You let catamorphism do the sort of bookkeeping of recursing down into the structure for you. Yes. So, 1044 now. We're going to be diving more into recursion schemes a little bit, and then showing how to actually use this to do a simple diffing algorithm in the next session, which, yeah. Let's actually, does anyone else have any more questions about catamorphism? We do have some, okay, cool.
Yeah, can you switch back to the definition of list f? Or
Absolutely.
yeah, so the functor instance for list f here, it's not like it works on B, right?
Yes.
The recursive part of the list f.
Yes.
I think that's important.
It
Because
is.
normally for a list, you would assume it will work off the elements of the list, but
Right,
it
right, right.
works off the recursive part.
That's a very good point, yes. Yeah, the functor is over listf of A and is used for the recursion schemes bookkeeping. There's a very good reason that no one actually defines functors or defines list like this. The sort of goal here is just to give you an example of like sort of a list that seems like semi-familiar. And then we're going to jump back to a directory layer and show how to do some interesting things with that.
Yeah, but I think this point is very important to understand what the f-map is doing in Kata.
That's a very good point. Yes, I should have highlighted that a bit more. So again, you're f-mapping over the B, not the A. And this is why lists in Haskell are not defined like this. Yeah, so again, looking at that, right? You're starting with the x, the fix of cons1, fix nil. You're unwrapping the fix, you're getting rid of this, so you just have cons1, fix nil. Then you're f-mapping over this, you handle just fix of nil with your, and then again, you unfix it. You f-map, it does nothing because it's nil, it doesn't have any recursive link, there's no B or no A, but that doesn't matter. You apply your algebra to this, you collapse it down to a list, empty list case, as you can see here, right? It hits the algebra nil case. And then finally, you have a cons1 empty list that you then apply your algebra to again, and then you just prepend the 1 to the empty list, and you get a list of 1.